the basics of how AC works. As you guys started into the lab, we're dealing with resistors. It's going to follow the exact same rules that that regular DC does. The only difference is when we start getting into capacitors. So as far as theory goes, we're not going to necessarily cover resistors because we've already covered them. So what we're going to do is we're going to introduce how capacitors work, but we can treat them like resistors once we get them into a certain format. And then everything is going to be the exact same that what we would do. Come on, where's my note paper? And I think, and while we do this as well, what will happen is we'll also introduce the concept of phase shift. So we'll kind of do these together. We're only going to be dealing with capacitors in the circuit. We're not going to be dealing with resistors and capacitors. So either way, these will work with either just resistors or just capacitors. So the circuit that we have, we will start off with this guy. Oh, I know. Trust me, I've done it about 3 or 4 times, writing down notes. I get going, I'm like, ah, crap, that's a DC supply. I don't want that yet. Why did I do that? I don't want that either. Just capacitors. RC circuits, resistors, and capacitor circuits will be next week. All right, so we have capacitor 1, we have capacitor 2. Capacitor 1 is 15 microfarads. Capacitor 2 is 150 microfarads. We have 10 volts peak. And so one of the things we're going to do is, what we're going to find in AC is these guys are going to change their effective resistance, which is the reactance, according to the frequency. So we're going to analyze this circuit using a couple of different frequencies. We want to find out, let's see, the voltages, the reactances, the reactance totals, and the voltages of each of the capacitors. So remember in our list, these are what we're going to be working with from here on out. So reactance is going to be measured in ohms, just like resistance. But remember that reactance is the imaginary version of resistance. Okay, we're going to treat it the exact same, other than it's not going to add directly with like resistor resistance, but reactances will all be added together the same. And so that's why when we're doing this, we're still using resistance. We're just getting it a different way. We're going to use impedance, which is our total resistance and reactance, and we're going to be using our capacitive reactance specifically, because we're dealing with capacitors. Next week or the week after, we will deal with inductive reactance, which is dealing with inductors. So with our circuit that we have, what we're going to do is we're going to build us a chart for our data. So our frequency is going to be in hertz. We want to measure or calculate the XC1 in ohms. So the reactance of capacitor 1, the reactance of capacitor 2, also in ohms. We want to get the voltage of capacitor 1 in volts and the voltage of capacitor 2, also in volts. So what we're going to do is we're going to be using 100 hertz, 2,000 hertz, and 10,000 hertz. And we're going to track what happens with the circuit. The other thing that we also could do, and I'm kind of out of room, we want to calculate what our current is. So again, with our base circuit, we're going to go through and solve these guys. First thing we want to do is we start with any of them. But let's start with our 2,000 hertz signal. So a 2K hertz, just to start with as our base. And then we can kind of compare what's going to happen when we decrease our frequency, when we increase our frequency. Now, the first thing we have to go through is solve for the reactances of each of the capacitors at each frequency. Yes? Yeah, 2,000 cycles per second, yes. Yep. Yeah, so we'll have a positive peak, a negative peak, and that's going to happen 2,000 times a second. Okay, so as we're looking through this, the formula that we're going to use is based on our capacitive reactance. It's going to be X of C is equal to 1 over 2 pi Fc. So we take 2 pi times our frequency times the actual capacitance. We take the inverse of that. That's going to give us the resistance, essentially the resistance of our circuit, of that component. So the capacitive reactance of capacitor 1 is equal to 1 over 2 pi Fc. We plug our numbers in. 1 over 2 pi times our frequency, which is 2K, times the capacitance, which is 15 microfarads. That's going to give us a value of ohms. Did you do the 100 or did you do the 2K? Okay, we're going to start with the 2K first. That's okay. $4.7? 5.305 is what I got to. Yep. Make sure all that's in parentheses. Because my guess is that times 10 to the negative 6 got taken out and multiplied against everything else. At the very least, that's what happened. $5.305. Okay. One of the other things that we also have to take into account now. Oh, just straight? Okay, so we have 5.305 ohms is all that guy is. Now we have to remember, when we're looking at this guy, we have to remember exactly what we're looking at. We have a real component, we have an imaginary component. In this instance, is there any real component to this capacitance? No, it's all capacitance. So what we're going to see is our phasor diagram is going to list it as this. So we've got XC1. Now we have to indicate that this isn't resistance. So what would be our angle if we're assuming resistance is equal to 0 degrees? Negative angle, okay? Because we're here, we go up, we're going to go positive angle. We go down, we're going to get a negative angle, okay? So what this becomes, nope, that's the magnitude. So what we're doing is we just built this vector point right here. And we're going to list it as both in its polar notation and its rectangular notation, okay? So again, like we said, we have no real component. It's all reactive, okay? So this is negative 90 degrees. This will become important when we start tracking these guys. Because we're down here on this axis, 0 is our center point. It doesn't go to the right at all. It goes straight down. It's always 90 degrees out of phase from the base resistance. Okay? So what we have now, this is our polar notation for this, essentially this resistance value. It would be positive 90. But inductors are special cases. They have their own rules that kind of apply to them because they also have a resistive component to them as well. So the inductance itself is positive 90, but then you have to add in a little bit of resistance. So it shifts it. Yep. Okay, so the other thing that we have, so if we have this value here, it's sitting right on this axis. What is the coordinates of that point? Rectangularly. Okay, this is our rectangular. Okay, using the notes that we talked about last week and the week before about going back and forth between polar and rectangular, we can prove that this value equals 0 minus j 5.305. Okay, so like I said, we're going to take a lot of time working on this problem because I want you guys to understand this is how everything ties together. The biggest part is we are just trying to get this value. These angles are not so important right now, but when we start adding in resistance, they will be. So I want you guys to get used to using them before we start making them super complicated. Okay, so who remembers what's our formulas to go back and forth between polar and rectangular? And if not, we can always draw the pictures up. It's not, we don't have to worry about it. We're going to use the same graph right here. Okay? So I'm going to draw our triangle and make it match what we're using as far as our coordinate system. This is the real value. This is the reactive value. This is the total combined. This is our phase angle right here. Okay? So if we were to work backwards, let's say we have this value. We have our polar notation. We have this value. We have this value. We want to solve for our R and our X value, our real and our imaginary. Exactly. Okay, so we have, so let's look at one of those guys. So the sine of theta is equal to the opposite side, which is our x, over the z. So we take the z sine of theta to give us our x coordinate. Okay, we use cosine is equal to the adjacent, which is r, over our total. To get the real value. Okay, so when we take our 5.305 times the sine of 90 degrees, what does that give us? When we take the negative 5.305 times the cosine of negative 90, gives us 0. So going back and forth between 90 degrees, 0 degrees, and positive 90 degrees is really easy. Because all we have to remember is if we're at positive or negative 90, we don't have any real values. So it's just that value, plus or minus, depending on which side of it is on. Capacitors are going to give you negative J values. Inductors are going to give you positive J values. So now we can go back and forth between these. But also remember this little trick. If it's at negative 90, you have no real, it's all capacitance. If it's at positive 90, you have no real, and it's all positive J. Does that make sense? Okay. So now we have our first value. We have 5.305 at negative 90. Okay, now we want to go through and we want to solve for the XC2. So again, 1 over 2 pi times the frequency times the capacitance. So we have 1 over 2 pi times 2,000 times 150 micro. What would you guys think is going to happen? Is it going to get bigger or is it going to get smaller? It's going to get smaller. Because the capacitance went up by a factor of 10. So if we're increasing the denominator by 10, we're going to decrease our answer by 10. Divide it by 10. Oh, 200 hertz. That'll do it. Okay, so now we can come back and look. Does anybody have a problem with how we got this value? So now we have these values. What are they in terms of? They're at negative 90, but what unit are they measured in? Ohms. We can treat them just like resistance at this point. The only difference is they have a negative 90 attached to them instead of a 0. All the other problems we've been doing, we've still been doing the same method, but we've been ignoring this part because it's 0. And 9 times out of 10, when it's 0, things like that, we can ignore it. Okay? Now we have to keep track of it. So now that we have these values, they're in ohms, we can treat them just like regular resistance. Okay? And especially when the capacitors are together, we can use all the same tricks. Voltage divider. We can solve for current without any problems. Okay? Yes? In what? Use a resistor? You could, but you're going to get phase shifts. If you don't care about the phase shifts, then yes, you absolutely could. Those will go into the calculations. But the biggest thing is when we're solving for these guys, as long as they're in the same phase, we can use things like voltage divider because that doesn't care about phase. You cannot use that. What we're going to be doing is solving back and forth using these conversions. So this is polar to rectangular, and then we're going to have to convert back and forth between rectangular to polar as well. So again, when we get to that point, I'll show you. Because when we're in rectangular, what math functions can we do with a value? Who remembers? When you're in rectangular notation, which math functions can you do? Add, subtract, multiply, divide. The 4 basic math functions. In rectangular, what can you do? There's 3 of them. You can multiply. It gives you a weird value, and you have to do some extra conversions, but you can multiply in rectangular. You can add, which means you can subtract. You cannot divide very easily in rectangular. You can, you just have to go through and use the long division that we learned a 3-4 weeks ago. Okay? It's not very easy, it's not very friendly. So you add and subtract in rectangular, and why would you want to add and subtract values? Yeah, you got 2 currents. You want to add current and subtract current. You can do that. What about series? Resistances. You add and subtract. You add series resistances together. We have series resistances. So it's going to be the same thing when we get to capacitors. We're going to have values that we want to add together. So we're going to have a real resistance and a reactance. We're going to combine those together. So we have to have them in rectangular so we can add and subtract. Yes? If you're given those, you just have to have your frequency. Okay? You multiply and divide, so basically Ohm's law is multiplication and division, you want to use in polar. And we'll show you how to do those. So the first thing we want to do is we're not going to, we could use voltage divider, and we'll use that as a double check, okay? But we want to solve for the voltage drops across each of these capacitors, and then we also want to get our current total. So what we have is we need to solve for the voltage of these guys. So we have the reactance total, because that's all we have, XCT, so reactance capacitors total, is going to be equal to the reactance of capacitor 1 plus the reactance of capacitor 2. Okay? We already found that we had 5.305 at negative 90 plus 5.305 to the negative 90, or sorry. Yeah, we'll add those guys together. So in this total, what we have to do, remember, we can't add in rectangular. It's not possible, so we got to convert these guys to rectangular. So we plug these through, but we also know our trick. We convert these guys to rectangular. You can, but just as a general rule of thumb, convert them back to rectangular, then add them together. Just in case they're different. If the angles are the same, yes, you could just add them straight across. But I want you guys to get used to understanding that you have to convert it to rectangular to be able to add them together. The what? The angles come from this relationship. So resistance and reactance, real and imaginary. So they're on the different axes. Capacitive reactance is down here below our real value. Inductive reactances are above it. So if it's just pure capacitance, it's negative 90 degrees. Yes. Yeah, not right now. We're just dealing with just capacitors or just resistors. Yes. Yeah, I'm making it really easy for you guys. More or less. I know this is a lot of information, but like I said, I want to go through this step by step to get you guys used to solving them this way. Yeah. So now we convert these guys to rectangular because we just want to make sure we add these up correctly. And so now we combine real and imaginary, and we end up with the 0 minus j, and what was the value, Max? Okay, so that is our reactance capacitance total. It's also our impedance total because we have nothing else in the circuit. That's it. Okay, so the reactance and the impedance in this case are the same because there's no resistance. If there was resistance or inductance, we would have to go through and solve for that. But right now, it's not here. So we have this value. Well, now the last thing we need to solve for, or the other things we need to solve for, is the voltage and the current. Those require which law? Ohm's law. When we're in Ohm's law, what do we have to do? Which functions? E over I, V over R, multiply and divide. Okay? So we need to convert this number, because it's in rectangular right now, we need to convert it back into polar so we can do our multiplication and division. Okay? So to convert back from rectangular to polar, remembering that these guys, this is polar to rectangular. Again, we're going to be basing it on our trig identities. Okay? What was the one that we didn't use? Tangent. So we have the tangent of theta, referencing back to this triangle. So the tangent of theta is the opposite over the adjacent, so x over r. Are they the same though? How much resistance do, what's our real value? Is what? Yes, in that case, x over z would be the same. So we need to find this value. This is going to give us we take the arctangent of both sides. That'll eliminate the tangent on the one side with our theta. We take the arctangent on the other side of our x over our r. That's going to give us our theta. Yes. 0. Real, imaginary. So we have real plus or minus jx. Hmm? Okay?
Well, then it's just the whole number.
It's the whole number.
Not dividing it. It's just that part over 0, which is that number.
This is one of the shortcuts we have to learn. You're right, we can't divide by 0. Okay? When we have no resistance, remember, we're on this line. Which means we can't make the right triangle, but that's why this fails. But we have to remember, if r equals 0, if r equals 0, then our angle has to be equal to negative 90. That's just one of the identities that we can find. In calculus, you guys will go through this and actually prove to get this value. Because in calculus, you can divide by 0 in certain circumstances. Yes. Not a lie, it's just special case rules. Basically, this is going towards you have an asymptote. So that's why we use calculus. The world will explode if you try to use algebra to divide by 0. You can use calculus. Yes. Yes. It's a negative 90 because remember, capacitance is below our real line. So it's a negative 90. This was kind of a trick question based on this problem, just so you guys know. We just have to understand and accept that when we have just capacitance, the angle is going to be negative 90. Okay? When we have just capacitance, the angle is going to be negative 90. Then we'll start seeing it shift and you'll actually get answers coming out. Okay, so now that we have this value, we need to solve for the z. How do we get the magnitude of our angle? Okay, remember we have our triangle. We just found this value. We need to solve for this value. We have our real. We have the reactance. This value is solved for. How do we get that value? Not sine. Pythagorean's theorem. Okay? Okay, a squared plus b squared equals c squared. This is where we can take into account the 0. So we have the square root of r squared plus x squared equals the impedance. What happens when we take the square root of a square? It falls away. That's the other nice thing is when we have this guy, this value, when we don't have anything, is going to just translate over. Just like what we found here when we translated it over this way. When we're not adding another component, that value just transfers. The sign follows and the magnitude transfers over. Yes. So our impedance is equal to 5.8355. Okay? So we have our capacitive total is equal to 5.8355 at negative 90 degrees. Again, this is a long way around to get to it. Just get used to seeing if you have no real component and you have a reactive component, it's going to be this value plus or minus 90 degrees dictated by the sign of the J. If you have 5.835 here in your real value and 0, you're going to have this value at 0 degrees. It's just because at that point it's all resistance. There's no reactive components to it. So now that we have this value, this is also equal to impedance because we don't have anything else in the circuit. We have capacitor 1, capacitor 2. They're both reacting to the frequency and creating a resistance in opposition to the AC current. Now we can solve for all the voltages. First, what's our current? How do we solve for current? What's the formula? V over R, because we want volts divided by ohms. So in this case, we can substitute this impedance in for R, because it's the total opposition to this circuit. I'll show you. Okay? So what was the voltage that we had? 10 volts peak. And it's very important that we know that. We have 10 volts peak. If we're not given an angle, assume 0. Okay? We divide that by the 5.8355 at negative 90. So we have volts, we have ohms, we're going to get current in amps. Okay? So the real numbers are going to just divide. So you take 5 divided by 5.8355, and what does that give us? Amps peak. Okay? And now, the easy part. When we're dividing, when we're multiplying, dividing degrees, treat them like powers of 10 exponents. So we have 0 minus a negative 90 gives us positive 90. The degrees are easy because if we treat them just like exponents, we add and subtract based on if they're multiplying or dividing. If we're multiplying them, we will just add those degrees together. If we're dividing, we subtract those degrees one from another. So in this instance, we have 1.714 amps at 90 degrees. So one of the cool things that this means is in this circuit, if we had the ability to graph the current, we would see the current would spike at the very beginning before the capacitor charges. Once the capacitor starts charging, once it hits full charge, what happens? It'll discharge, but what happens to the current? When it hits max charge in DC, what happens? Current stops. It turns to an open. Then the AC starts going the other direction and gives it a chance to discharge. And so what happens is this current, you're going to see the most amount of current when the voltage of the capacitor is the smallest. And then when the capacitor of the voltage of the capacitor is the largest, you're going to see the least amount of current. Then you're going to see it shift the other direction. So your current is going to be 90 degrees ahead of what your voltage is doing. It's kind of a cool little phenomenon that we get with these capacitors. Okay? So we have 1.714 amps at 90 degrees. Now we need to solve for the voltages. How do we solve for voltage in a series circuit? Voltage divider or current times resistance. Currents for parallel circuits. Okay? So now, what current do we have going through capacitor 1? 1.714 amps. What current do we have going through capacitor 2? 1.714 amps. So the voltage of capacitor 1, again, is current of capacitor 1 times the reactance of capacitor 1, because we're dealing with the ohms. Yep. So we take 1.714 volts, or sorry, amps peak at 90. The voltage is going to end up being at 0, which is what we would see when we'd measure it. Because it's at 0, the current's leading. Yeah, you're going to multiply these guys across. So when you have just capacitance, you're not going to see any phase shift in your circuit. Just like you wouldn't see any phase shift if all you had was resistors. For those of you that have started on the third part of the lab, actually measuring the signals, isn't that what you're getting? You're getting peaks that happen at the exact same time, and everything's adding together. On your screen, when you're measuring it, isn't that what you're getting? It's the same thing with all resistors or all capacitors, or even all inductors. They're a little bit harder to match together, but you'll get the same effect. Everything's going to be lined up. There's no phase shifts whatsoever between all capacitors and all resistors. Yeah. And like I said, that's why I wanted to go through step by step through this one. Then we'll go through another one without quite as much of all the excess stuff. Okay? So what does the voltage drop across this guy? How much? Okay? Now with that, what would we expect the voltage across the other capacitor to do? It's going to be 997 milliamps or millivolts. Because everything is at the same phase angle. So we could just add and subtract like we would normally. So the voltage for capacitor 2, 10 minus 9.093, okay, let's double check it. 1.714 amps at 90 degrees multiplied by 0.5305 at negative 90. So Ohm's law proves it. Kirchhoff's law proves it. We still have those two rules still in effect. Okay? All we've done to our equations is now we've added in, we have to keep track of the phase angles. Nothing else has changed. The other thing that we've added is, we're still dealing with ohms, we're still dealing with volts, we're still dealing with amps. The only difference is we have a capacitor that we have to do one extra step to find essentially its resistance, its reactance to AC. Okay? So we'll come back up to our chart and we'll put in these values. Okay, and the current we had 1.714. Come on. At 90. Okay, now we want to do and just check to see what's going to happen with this circuit. So now when we do a current, so what I'm going to do is I'm going to split the room up. Okay, I want this side to do 100 hertz. I want this side to do 10,000 hertz. Okay, so again, we're going to work through the same steps as before. Okay, well, I'll solve the first one for the 10,000 hertz guys. Okay, so the first step we need to do is to solve for what is the capacitive reactances of each of these capacitors. Okay, so again, come on, stop doing that. So I'm going to switch colors. Yes. So X of C is equal to 1 over 2 pi times the frequency times the capacitance. Okay? So X of C1 is equal to 1 over 2 pi times 10K times 15 micro. What are we expecting this to happen? We've increased the frequency by 5. So what should it do to our reactance? Should decrease it by 5. Still going to be at a negative 90 degrees. Okay? At 100 hertz, XC2 or XC1, 2 pi times 100 times 15 micro. Our frequency has done what at 100 hertz? It's gone down by a factor of 20. Okay, because we've gone down by 10 to get down to 2,000, and then we cut that down, or from 2,000 to 100, and then we cut that in half. So it's gone down by 50. So we've decreased it by 50, so we should see this increase by the same value. Okay, so what does our X of C1 come out to be at 100 hertz? At negative 90. Like I said, I'm getting you guys all the building blocks. We want to make sure we get our angles in. So now we're going to go through and we're going to solve the rest of these the exact same way. We have to solve for our X of C2 for each of these the frequencies, so on your respective sides. Then we're going to add these guys together to get our capacitive reactance total. We take that value divided into our 10 volts to give us the current. We take that current multiplied by the individual reactances to get our voltages. I think that covers most of the information as far as the notes, other than finding XC1. Yes. This is the very first quiz. Yes. Okay.
We just like plug it into the same equation.
Same exact equation.
And would it be at negative 90 too? Or?
Would be at negative 90 as well, because it's capacitance. Every capacitor, when you find its reactance, is going to be at negative 90. Every single one of them. Inductors are a different story. Any capacitive reactance will be at negative 90 degrees. Every time. So when you add values together, like if they're in polar, they're both going to have the exact same phase angle, so that phase angle will carry through. You won't do anything special to it. Mm-hmm. Mm-hmm. The negative, yeah, the zero negative j or 0 - j of some value is negative 90 degrees. Some value plus or minus 0 is 0 degrees, and then plus 0 plus j of a value is positive 90 degrees. Yep, inductance. Yes, that's what we'll be doing that next week. I know it's a lot. I know I'm expecting a lot right off the bat. But like I said, we'll go through this and we'll work through it again. The cool thing is there's very little that actually changes in these circuits.
I looked at the quizzes like Monday morning, probably yesterday morning, or Sunday night, I can't remember. There's all these variables and like max and stuff. I didn't recognize any of them. We have like X now, like XC, find XC1. I'm like, we'll work on it some other time.
And that's okay. That's honestly, that's what I want you guys to do is open up the quizzes, look at them, because then you're going to be like, okay, how does this work? And then you have questions that we can be able to work through.
It was so much I didn't even know, man. I just opened up that first quiz. The very first quiz. Read the little labels for the answers, and I was like, well, this is not going to be able to be done in the next hour. I have a question.
Yes,
Where did the frequency values come from?
I just picked them.
If we're taking a quiz, will it give us the intended frequency value?
Sometimes yes.
No.
It'll give you, I want this one to be this value. What frequency do you have to use to get this value?
Oh my goodness. That's a whole different level, bro.
We have to backwards calculate.
Mm-hmm.
What about the forward calculator? Will that be before the end of this week, or will that be later in the
Oh, it'll be this week. Essentially, yes. Because we don't have a test this week. Next week's test is going to be over this material. Nope, just one test over the previous week's material. Okay. Let's start solving this together. Okay, so we have X of C1 is 1.061 ohms for our 10K. Okay, X of C1 for our 100K or 100 ohm. So let's go through with our 100 ohm guys or 100 hertz frequency guys first, and then we'll come back and do the 10K. So I'm going to switch over to purple. XC2. What's the formula for solving for the reactance of capacitor 2? 1 over 2 pi times frequency times capacitance. 1 over 2 pi times 100 times 150 micro. Okay, what did we get for the reactance for capacitor 2? Okay, at negative 90. Okay, so now that we got X of C2, what is our capacitance total? Our capacitive reactance total? 0.7 what? At negative 90. That's also the impedance total because that's all we have in the circuit. Okay? Current total. Capacitive reactance. How much?
85.68 milliamps.
Okay, voltage of capacitor 1. What do we get? 9.09 volts. At 0 degrees. All right, so X of C2 is 10.61 at negative 90. The total is 116.713 at negative 90. DC1 and VC2. How much is VC2? Okay. Everybody's good there. Okay. 10,000 hertz. What is our X of C2 and how do we find it? And how do we find it? Okay. Everybody good with that? Okay. What is our capacitive reactance total? 11.61. 1.161. Yep, because we only have one there and we've got 0.1 there. Okay? At what angle? Negative 90. I total is? And how did we find that? Reactance. And then the voltages? 9.091. C2? 0.909. Mm-hmm. As far as these values, or? Well, what changed? The frequency. The capacitance didn't change. So the ratios stayed the exact same because we use the same formula for all the capacitances. So when we change formulas, or when we change frequencies with capacitors, it's as if we were using resistors. The ratios are going to stay the same because all we're doing is changing one of the variables, and that's just the frequency. But both of them is changing with the same rate. So with that, like I said, this is where the capacitors and resistors are the same when we use just capacitors or just resistors. All we're doing is just changing the total current. That one's fluctuating, but the voltages are staying the same because we're keeping the ratios the same. So reactance works the exact same as resistance. Okay, we're still going to be dropping different amounts, or the ratios is going to be what determines how much is dropped. Okay, so not necessarily with like so when we get into RC circuits, we're going to see these ratios switch because when we change the frequency, what happens to the resistance when we change frequency? What happens to resistance with frequency? Resistance doesn't. Reactance does. Resistance doesn't care what frequency you put it through. If you put 10k hertz versus 1 megahertz through a resistor, it's going to have the exact same value. What's going to be changing is the reactances of these components. So when we start intermixing those, then we're going to start seeing that 1,000 ohm resistor we put in series with a 10 microfarad capacitor, it's going to be changing because the resistance will stay the same, but this reactance, as we can see here, changes based on the frequency. So when we have just capacitors, it doesn't matter what they're changing to, they're going to maintain the same relationship. Same thing with resistors. If we change the frequencies for resistors, we're not going to see any difference with the voltages. Okay? What if we had stuck, instead of You know 106 ohm, or the capacitor, the 15 microfarad, and we had the 150 microfarad. What if instead we just used a 106 ohm resistor and a 10.6 ohm resistor? What would happen to our circuit? It wouldn't have any reactance because now we're using resistors. But what would be the phase angles of the currents, voltages, and all that other stuff? It's going to be 0. So we're still doing these exact same steps. It's just this is going to be 0. Divided by a 0 is going to give us 0. Multiplied by zeros are going to give us 0. Just on the triangle because everything is based on 0 at that point. Yes? Yeah. We're changing the peaks, and so this is how we have to report stuff in voltage peak. Because this voltage is always changing, we could just say this voltage, and it could be anywhere on the sine wave. So that way we can measure it is we want to go with our peak or peak to peak. Generally, when we're looking at stuff on a scope, we want peak values. Those are easy to find because for one, your scope will do that automatically. It'll tell you the peak voltage. It'll also tell you the RMS, but it's off sometimes. But the safest bet is to do everything in voltage peak. Okay, what if we didn't have a voltage peak? What if we just said 10 volts? What do we need to assume? It's in RMS. So then we have to convert that into peak. Root means squared. You divide it by 0.707. Okay. So like I said, this was just an exercise to show you guys that when it's all capacitors, they function and behave just like resistors. So in lab, when you're doing these, you're going to do the exact same steps except for these guys. Because we don't have any capacitive reactance. You are already given the resistance value. We can measure that. You could. You just have 0 farads of capacitance. So it comes out to be 0. Yeah. The fun thing is, there is actually capacitance in your circuit, whether you want it there or not. Because when you're putting, because think about it, if you're putting things in your breadboards, yeah, so you've got these little clips that come up like this. Whatever. They're supposed to be lined up better. I can do better than that. That's a horrible drawing. Okay, so when you have these clips, you put in the lead for your resistor, goes into this hole. You put in another lead to your resistor. Okay, what do you have now right here? You have a capacitor. You have 2 pieces of metal in close proximity together. You do have a little bit of capacitance. Negligible for what we're doing. Like we're talking pico and femto farads of capacitance. Teeny, 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 tiny amounts. What we'll see this capacitance come into play is when we start doing filters and resonance and stuff like that. That's when you'll see this capacitance come in. It's actually pretty cool. You'll build a filter and you're going to think it's just a high-pass filter. It's going to allow any kind of high frequencies through it. The problem is, once you get up to a certain frequency, this little guy becomes very, very large. And then it starts gobbling up all the frequency or all the voltages on this point. So now what you thought was essentially a high frequency, let it high things go, it's going to cut it off at some point. But there's no way we can get around that. But for all intents and generals, it would be a high pass because it's letting high frequencies, except for the ultra high frequencies, compared to what we're looking at. Like I said, that'll all make sense here in about 4 weeks when we start talking about that. I'm just trying to give you guys why we're doing this, why we care. So, and then I'll let you guys go to break here in just a second. So with our circuit, that's why I wanted to do capacitors as well, because it also deals with the phase angles. It deals with converting back and forth between polar and rectangular at times. but we can treat them just like we would resistors. You could go through this exact same thing and calculate all the phase angles based on resistance. But in this case, all the phase angles would be 0. And with capacitors, they alternate between positive or 90 degrees, depending on if you're looking at current or voltage. One way to remember this is the acronym ICE. Current comes before voltage in capacitors. So your phase angle should be a angle bigger than your current angle. So that's kind of another double check that you can have. If your current comes out to be a value of the angle less than what your voltage is, there's something wrong. Current should always lead your voltage as far as phase angle goes in a capacitor. And this is the key that it's a capacitor. We have another acronym for dealing with inductors, and it flips. Okay, let's go ahead and go to break. I know you guys' brains need it. So go ahead and take a break, and then we'll come in and we'll work on another one of these problems.